All right, so we jump into a new chapter today, basically dealing with radicals, exponentials, and logarithms. So that's coming. A little more Algebra 2 centered review. Today we're going to look at our exponentials and radicals, and we first got to look at our properties of exponents, and we know all these from basically Algebra 1 and Algebra 2 for the most part. If we have two quantities with the same base, and notice the base being what's raised to the power. If those two are exactly the same, then we can take and add the powers. If I have what I call a power raised to a power, then we multiply powers. Two terms with, once again, the same base, and they're divided, we take and subtract bottom from the top. These b's within the radicals, those are called indexes. And if you have the same index, then you can just take and multiply the two radicals together. And lastly, if we have some index of a base raised to a power, that's the same as writing, going from radical to exponential form of the power over that index. So the index acts as the denominator of the power. Let's do a couple of problems now. These are meant to be done without a calculator, and we're finding exact values. We want to write, first of all, this in just exponential form. Now there's an implied 2 within square roots because we're asking what multiplies by itself. So the power of 30 is 1 since there's nothing there. Therefore, this is like 30 to the 1/2 power. Pretty straightforward. Now if we were to take this next one, and we know that the index acts as the denominator, that gives us x to the 3/5 and y to the 12/5. Both carry the same guy. That could also be written as x cubed y to the 12th, all raised to the 1/5. And then we have a power of powers, so we multiply the powers together. Either way. Now we're going to be asked to simplify these, and again, non-calculator, do this in exact values. So we may have radicals in our answers, or they may actually come out easy. What I like to do is I like to break this down into square root because I see my index of 16, and I can say that's cubed this way, or I can write it as a square root of 16 cubed this way. Because once again, this is just, I could say 16 to the 1/2 cubed. And 16 to the 1/2 is just square root of 16. So that's why I get to do that. Square root of 16 is 4. Cube that, and I get 64. Done. Now, this problem has a negative exponent, and we know negative exponents mean to take the reciprocal. So this is the square root of 8, all raised to the 2/3 power. And I know the square root of 8 is the same as 8 to the 1/2 power. And that's all raised to the 2/3. Power raised to a power, I get to multiply my powers together, so that's 8 to the 1/3 power, which is the cube root of 8, which ends up being equivalent to 2. Next, we'll simplify the cube root of 81. And just like when we're simplifying square roots, we want to find the largest perfect cube that goes into 81. 27 is that number. So the cube root of 27 and the cube root of 3 multiply into the cube root of 81. The cube root of 27 is just 3 times the cube root of 3. And that would be our simplified form. In this case, our indexes are the same, so we can't multiply 8 by 4. We have to get the same indexes, and that's going to be kind of difficult unless we change the form we're in. Right now, we're in a radical form, and we need to go to exponential on each of these to have any kind of luck. And we still have the same problem because our base now isn't the same. If our base was the same, we can add the powers. But here's the deal. While the base isn't the same, I know 8 can be expressed another way, and I know 4 can be expressed another way. In fact, 8 is the same as 2 cubed, and 4 is the same as 2 squared. So notice I have powers raised to powers. I can multiply those powers together, so I have 2 to the 3 halves times 2 to the 2/3. And the deal is now, notice, I have the same base. So all I have to do is add the powers. So I have 2 to the 3 halves plus 2/3. And now we just get common denominators of sixths. So this goes to 9/6 plus 4/6, which gives me 2 to the 13 over 6. Now, if I asked you to put this in radical form, this would not be in simplest form. Take a peek. I'd have the 6th root of 2 to the 13th. And the 6th root says for every 6 of these 2's, I get to pull 1 out. So I get to pull 1, 2 out, and I have 1 left on the inside. You'll notice 2 to the 6th times 2 to the 6th times 2 equals 2 to the 13th. And for every 2 to the 6th, I get to pull a 2 out. Let's move on. Now, in this case, again, we're asked to multiply two things together, having exponents, but they don't have the same base. But we're going to use the same principle we just used. We're going to name 4 as 2 squared. And that's raised to the pi, multiplied by 2 to the 3 minus 2 theta. Power of power, multiply the powers, so that's 2 to the 2 pi times 2 to the 3 minus 2 pi. And anytime we have the same base, we add the powers. So that leaves me with 2 cubed, or 8. Next. Now in this case, we're asked to solve for x. And we notice that we have 2 to some power is equal to 2 to another power. Well, if this is true, then it's got to follow that these powers, since I have the same base, must be equal. So effectively, all we have to do is drop out the base on this, and we have 5x plus 3 equaling 2x minus 15, and it turns into just a linear problem. We've got 3x equaling negative 18, and x equals negative 6. And once again, the only reason we can do this is because our bases were the same. Thus, we can say the powers are equal. And the fact that there's only one term on the left side and one term on the right side. So let's take a look at some similar examples. Now, we have one term on the left side and one term on the right side here, but our bases aren't the same. However, I can use the principle that I've used prior and say 9 is equal to 3 squared, and that's raised to the x plus 1. And then I have 3 to the 4x plus 5. So power of a power, I get to multiply the powers. That's 3 to the 2x plus 2, which is equivalent to 3 to the 4x plus 5. One term on one side, one term on another side, same base, therefore the powers must be equal. So 2x plus 2 is equal to 4x plus 5, therefore 2x equals negative 3, and negative 3 halves equals x. Now, In this case, I need to somehow get the same base. Well, I see that 1/25 can be rewritten as 25 to the negative 1, because that's the properties of negative exponents. Take the reciprocal, make the exponent the opposite of what it was. And then I know that 25 is just 5 squared. So I have 5 squared to the negative. I'm going to take and multiply these powers together while I'm at it. Negative x plus 1 power, which gives me 5 to the 3x is equal to 5 to the negative 2x plus 2. Again, one term on the left, one term on the right, same base, set the powers equal to each other. 3x equals negative 2x plus 2, 5x equivalent to 2, therefore x equals 2/5. That's all we've got. Take and answer those questions on the forum, and we'll see you tomorrow.